Hello everyone, in this video we'll talk about the arithmetic operations. We'll see how we can execute addition or subtraction or any other operations. Before that, we will see the layout of the registers that we have on the Raspberry Pi 3 ARMv7 architecture here. So we have general purpose registers like R0 to R6 and R8 to R10. Then we have different special purpose registers like R7 is for holding the system call number, R11 is for it is a frame pointer, and R12 is interrupt procedure call, and R13 is stack pointer. So these normally used for the maintaining the subroutines within a program. And similarly we have R14 which is a link register. So R13 is stack pointer that usually point to the topmost element in the stack memory. And we have the link register is used to maintain the link between the different procedures or the different subroutines. Then we have R15, which is the most important register, that is program counter, that is always used to point the next instruction to be executed. So it holds the address of the next instruction in memory that is going to be fetched into the processor and it's going to decode and execute. So then we have current program status register that is used to hold different flag bits like negative flag bit, zero flag bit or carry flag bits. On the basis of what we can make different decisions to jump to different sections of programs. We will study this when we will discuss the branch instructions. And then we have floating point registers. The floating point registers and their operations, we have a specific different coprocessor residing in the chip, which basically perform the vector or floating point instructions operations. We have these single precision registers from S0 to S31. So we have 32 single precision floating point registers to hold the single floating point numbers, and which are basically mapped to the double precision floating point registers, which are D0 to D15. So that makes 16 double precision floating point numbers we can maintain at a time in a program. So this is the scalar bank and this is the vector bank. If you want to add or subtract multiple registers values at the same time, we can use these banks registers. And similarly for floating point coprocessor, we have a different status register that is used to hold its own corresponding negative or zero flag or carry bits flags values. Alright, so let's get started with the Raspberry Pi interface, and we will see how we can perform arithmetic instructions there. So I'll connect to my device now. So I have already opened my terminal here, and we have in my directory. So this is my path, and these are my files which I created for. So I will just create a new file. I will name it ops.s. So I will write a program which basically do some arithmetic instructions. So let's see .global main. We have main here. Let's move some values in the main and some registers so we can perform their operations, arithmetic operations. So let's say we have, I will use move instruction for that purpose. I will move in R1 the value 3 and R2 with value 18. Alright, and let's say we have add instruction. Okay, I want to add R1 and R2. So I'll write R1 comma R2. Alright, and for subtract I have sub instructions. For example, I want to update now R0 by subtracting the value 3 from 18. So I'll write R2 comma R1. If I would write R1 here and R2 here, means that will mean that I want to subtract 18 from 3, so that will result in negative value. But just for the sake of simplicity, we are just doing this way. And then we have multiplication instruction, so r0 comma r1, sorry, r2, and we have for division, for the timing we can do unsigned division, udiv r0 comma r2 r1, which means basically I want to divide 18 from 3, so I will have to place the 18 here and 3 here, right? The divisor should be here and the dividend should be here. Alright, now I will write the returning instruction to exit my program, which is bxlr. Okay, I will save it and quit it, and let's see if I can have to make any changes in Makefile. Okay, so I already have made some changes according to our program name, so this will help us to clean and make the binaries again executable again. So let's quit it and do that. So make. Alright, so now we have this value. If we just execute this file, alright, and see our result here, so what we'll see is 6. So 6 is the answer of the last instruction here, which was division. So in case we want to see these answers, so we might have to use the GDB debugger again, so let's use that. So I will use a GDB command here, /program name. Set started now. So let's start it from by typing the start command. Program is starting. So now just if you want to see the code here, you have to write the disassemble command, run it. So you can see this is the value here. So this is the R15 register that the program count is currently pointing here. This means this next instruction is going to execute first. Alright, and if you want to see the current values of the registers right now, you can see it. So I will write info registers R0, R1, R2 and R15. so R15 is my program counter. Alright, so R15, you can see it's currently pointing to this address. Alright, so R0 is currently 1 and we have some chunk values here. So if you want to execute these instructions one by one, we can use the command step I. Alright, so if you want to see by assembling it again, you can see that the first instruction is executed. Alright, and it's now pointing to the next instruction. So if you want to see the registers again, you can see that now in R1 register we have value 3. Alright, and the next instruction we should see 18. Alright, so I'll again run step I, assemble it. So it's pointing to the next instruction. So I want to see the values now. So I have now R2 with 18 value, 3 in R1, alright, and 1 in R0, and my R15 is pointing to this particular instruction. So let's now run this instruction. So step I again. Alright, so first instruction was addition, so I will now see the result in R0. Alright, so you can see that now the answer 21 is residing in R0. So this particular column is basically showing us the hexadecimal values. Alright, and this bit here, they are showing us the decimal values. Alright, and now let's see what's the next instruction do we have. The next instruction is subtraction. Alright, so let's execute it. Step I, and now see the registers. So now R0 has value 15. Previously it had 21 after addition. Now after subtraction it had now updated to 15. Of course you can do different registers that I mentioned, so like for example R4, R5, R6, R8. You can use those registers and see here. So if you want to see all the registers here, you don't need to mention here, it will just display all the registers. Alright, so this is all we have here: the CPSR bits, the program counter, link register, everything here. Alright, anyways, so I'll just disassemble here and see what's the next section. Okay, so next is the multiplication. So let's see the result. Step I. Now what we have in R0, we have 54, so product of 18 multiplied by 3. Alright, then we have the division instructions. So we will divide 18 by 3 here by using the udiv instruction. So let's run it. Now see the results, registers. So you can see now 18 divided by 3, we have 6 in R0. So that's how you can debug the instructions, and you can see different results. Alright, and if you want to put a breakpoint here, you can also do that. So for example, so continue, there's a command continue that will just complete all the program in one go. Alright, so exited with code 0. Alright, so if you want to start it again, so just write start. So it's starting again. Alright, so if you now disassemble, see it's again pointing the first instruction. Let's say if you want to put the breakpoint here in this particular point, so what you need to do is that you just use the break instruction space historic, and now you just need to write this address here because you want to put the breakpoint here. Alright, so you just need to write the address of any line where you want to put the breakpoint. Alright, in case you want to run the some part of the program in a one go, and then you want to stop at some certain point, so that's a breakpoint. So that's how we can do it here. Alright, so I will just put break here on this particular address, which is 0x00103E4. Alright, so you can see that the breakpoint is at 3 at this address. Alright, and now if you just want to execute this program till this particular instruction, okay, it won't run, but it will stop here, so it will break here. So I will just write continue. Alright, at this particular point, if I want to now disassemble it and see where it has reached, so you see, so this instruction still has to be executed. If you want to see the status of your registers again, for registers, so we have R0, R1, R2 and R15. Alright, so you can see that the last instruction, because it was executed the multiplication, so answer is R0 is 54, rest of two have 3 and 18, R1 and R2, and 15. R15 has now the address of the next instruction, which is the division instruction. Right, so if you just want to execute it, alright, okay, so there's a problem, test detected. Now anyways, if you just write continue, so it's still having the problem at udiv instruction. So in the start of the program it didn't occur, now it's occurring. So let's quit it. Alright, we can start it again. So let's start it again, and so send it. Okay, I will put the breakpoint again here at this instruction. Alright, so write break static ux 0010 3e4. So this is my instruction here. It should reach here. I'll just write continue, enter it. Okay, now just see the registers again. So R0, R1, R2 and R15. Alright, and this assembly to see. So dev instruction still has to be executed. So now I will write step I. Okay, so it's again showing the error. Right. Okay, now. Okay, just let's go and start again. This time I'll put the breakpoint at one instruction before that. Alright, so let's see if it works or not. So start, disassemble. Alright, so this time I'll put the breakpoint here. Okay, so I'll say break static ux 00103 e0. Alright, I'll say continue. Alright, now this assembly here. So my instruction still needs to be executed, and now let's see the values as well of the registers. We have 0R1, R2 and R15. We have 15 here. So okay, now let's the step I again. Alright, let's see the registers values. Okay, it's 54, and now we have 6 instructions to execute again. Let's see step I. Okay, so it has worked now. So there's probably some error with the breakpoint clashing with the udiv instructions. I don't know why, but you can if you have to put the breakpoint like on dev instructions, you might have to end up putting the breakpoint just line before that. So maybe it will then work just as in this case we can see. Alright, so let's see the registers values. So here we have the correct value now as well. Right, so since we add the last instruction, okay, if you step you see that this instruction is going to be executed. So if you will put step I here, so it's going to take you somewhere else. Alright, again a long routine to exit. So we will simply write this continue command to end this. Alright, so that's how you have to do it. So now we can quit it. Alright, so you have seen that how we can use this debugger to see the different results. Alright, so that's all for this video. In next instruction we will see how we can use the branch instructions. Alright, so that's all for now. Thank you.